Let's look at this 3D particle equilibrium example problem. We have a 600 Newton force that is acting on a ring that is suspended from 3 cables. And the problem wants us to determine the tension in each of the cables, AB, AC, and AD. So I'm going to use 4 pretty distinct steps in solving this problem. First, I'm going to draw a free body diagram of the particle at point A. Then I'm going to express each of the forces acting on the particle at A in Cartesian form. Then I'm going to sum the x components of the forces and set those x components equal to 0, and do the same thing with the y components and the z components, which is going to create 3 independent equations involving the 3 unknown magnitudes of the tensions in cables AB, AC, and AD. And then the final step is going to be to solve those 3 simultaneous equations that have the 3 unknowns and solve those for the unknown tensions. So first, I'll set up my coordinate system, put A on there, and draw in all the forces that are acting on A. So I have the 600 Newton force acting straight down. I have the force AB that's in the XY plane, and it's 30 degrees from the y-axis. I'm going to call it FAB. Have FAC, which acts along the negative x-axis. And then I have FAD, which is in true 3D space. And if I look at the dimensions given on the diagram that came with the problem, I can deduce that force acts through the point, and I'll put it here, acts through the point where x equals 1, y equals 2, and z equals 2. Okay, so that's my first step. I've drawn a free body diagram of the particle at A, the ring at A. Now I'm going to express each force in Cartesian form. I'll start with FAB. Now let's look at what components FAB has. FAB has an x component here. Again, I'm going to draw it for convenience out here. and it has a y component here. And remember, this is a right angle here. Okay, so there's a triangle laying flat there in the xy plane whose hypotenuse is the magnitude of FAB and whose opposite side is the x component of FAB. So try to do this in color here. So FAB can be written as the vector FAB can be written as the magnitude of FAB sine 30I plus the y component of FAB is FAB cos 30J, and there is no k component for FAB because it's in the xy plane. Okay. Let's move on to FAC. That's an easy one. FAC only acts in the negative x or I direction. So we'll just draw this for completeness there and say that FAC equals minus the magnitude of FAC I. No J or K component. Okay. FAD is going to be a little more involved. So we know 2 points along the line of action of FAD. Remember that A is 0, 0, 0. So this is a vector, a force vector that acts along a known line. So I can write FAD as the magnitude of FAD times a unit vector, in the direction of the line between A and D, and it needs to be in the same direction as the force. Needs to have the same sense as the force. And I can write that as the magnitude of FAD times a position vector from A to D divided by the magnitude of the position vector of AD. Okay, now I'll just move this down to start a new line here. So FAD, the vector FAD is equal to the magnitude of FAD. I'm going to put a big bracket here. It's equal to 1 minus 0 I. I'm determining now, I'm calculating the position vector R from A to D, plus, and of course I missed a minus sign here, and this happens all the time. I didn't plan it. The coordinate out here that FAD passes through is not 1, 2, 2. It's 1, negative 2, 2, because the y-coordinate of that point is negative 2. So this is going to be minus 2 minus 0 j plus 2 minus 0 k. So that's the numerator here, the position vector from R to, the position vector R from A to D. Now the denominator is going to be the magnitude of that position vector, and that's going to be equal to, this should come down there, the square root of those numbers up above in the numerator okay, and that is the magnitude of the position vector RAD. And if you do all that math, you're going to get FAD, vector FAD, equals the magnitude of FAD times I minus 2j plus 2k all over 3, or FAD equals 1/3 FADI minus 2/3 FADJ plus 2/3 FADK. Now I wrote it like that because I know I'm going to end up with 3 simultaneous equations, and I need those coefficients out there, not contained in the parentheses there. Okay, so I have one more force I need to worry about, which is the 600 Newton force. So I'll just say 600 Newton force equals, and I got away from my color scheme here, that's in the K direction. So let me put this in blue. This is just going to be minus 600 K. And then go back up here to FAD. I meant to switch over colors. The K is blue. J is purple. And I is orange. Okay, so that's the second step. I've written the 4 forces, the 4 force vectors that act on the particle A in their Cartesian form. Now I'm going to go through and add together the x components of those forces and set them equal to 0, the y components and set them equal to 0, the z components and set them equal to 0. Now, why can I do that? Because for a particle in equilibrium, the sum of the forces, say the sum of the forces on A have to equal 0 if it's in equilibrium, And I can write that in terms of the three scalar equations. And let's just do those in color. Sum of the forces in the x direction have to equal 0. Sum of the forces in the y direction have to equal 0. And sum of the forces in the, let me erase that, make it look better. Sum of the forces in the z direction have to equal 0. Okay, so I will take those one at a time. So first, let's sum forces in the x direction. So I'm going to go through and pick out all my x components, which I've color-coded orange. Okay. So first I have FAB sine 30i, and the sine of 30 is 0.5, so I'm going to call that 0.5, and actually I'm going to do these in a different order so I don't get lost here. Apologize for this. I'm going to start with FAC. So FAC, the x component of the vector FAC is minus FAC I. Then I'm going to pick up the x component of, so I've got that one. Now I'm going to pick up the x component of FAB, which is FAB sine 30, and sine of 30 is a half, so I'm going to write that as 0.5 FABJ. Let's not start over, but I don't need to write I because they're all I, and these are scalar. This is a scalar. So it's just the magnitude of these components. Okay. And then I've got one more, which is the 1/3 FAD I component of FAD. So I'm going to write that as 0.333 FAD. Okay, and all that's equal to 0. Okay, so I've taken care of that. Now I'm going to go and sum my magnitudes in the y direction. And I'm going to pick up the FAB y term first, which is FAB cos 30, which I'm going to write as 0.866 FAB. Okay, so I've taken care of that one. And the only other component in the y or j direction is the minus 2/3 FAD here. So I'll pick that one up, and I need to be careful not to miss the minus sign there. And I'm going to write that in decimal, 0.667 FAD. Okay, so I've taken care of that one. And in the j direction, I apologize, the z or k direction, I'm going to sum those components and set them equal to 0. And I only have 2, which are the k component of FAD, which I'm going to write as 0.667 FAD. So I have that one. And then my last component is the minus 600 for the 600 Newton force acting downward. So I'm going to write minus 600, and that equals 0. Okay, that's the end of my third step. And now I have 3 equations, 3 independent equations containing 3 unknowns. So I should be able to solve those. And I'm going to call these equations 1, 2, and 3. Hopefully won't confuse things, and I'll call this equation 1, this equation 2, and this equation 3. And so at this point, you need to be good at solving simultaneous equations, or learn how to use your calculator to solve systems of linear equations. If you're using the TI-84, TI-83, there are lots of tutorials on how to do that, and it will save you a lot of time. It's worth the investment to learn it, and you're welcome to use your calculator for solving simultaneous equations on your test and homework and all that. So these, you might notice, are going to be kind of easy to solve because of the way the problem was set up. So I could put these in the calculator, but I see that I have in my z direction, I have just one unknown in the equation, so I'm going to solve that one first. So my approach here is to solve equation 3. I can write equation 3 as 0.667 FAD equals 600. And solving for FAD, I get 900 newtons. Now I can use that result to solve equation 2 using substitution. I can write equation 2 as 0.866 FAB equals 0.667 times FAD, which I just got a number for, which is 900. So FAB is 693 newtons. And then I can use those 2 results to solve equation 1. And I can write equation 1 as FAC equals 0.5 times the 693 plus 0.333 times the 900, and do that math and get FAC equals 646 newtons. Okay, so there are my three answers. Rounded. Remember, you can't round until the very end as far as doing the calculations. All that needs to be stored in your calculator. So let's just review the steps quickly here. This is a pretty typical 3D particle equilibrium problem. Step one was to draw a free body diagram of the particle at A. So here's step one. I'll put that in a box so don't confuse it with the circles. Step two was to express each of the forces that act on particle A in Cartesian form. So step two was all of this right here. Step three was to use the scalar equations, forces in the x, some of the forces in the x equals 0, some of the forces in the y direction equals 0, and some of the forces in the z direction equals 0, which are the conditions for are conditions for equilibrium of a particle. And we did that. So here's step three. And finally, we solve those equations. I did it by hand. You're welcome to use your functions, the power of your calculator. Again, it's worth the effort to learn how to, especially if you have a TI-84, TI-83, use the power of the calculator to be able to solve simultaneous equations, especially when you have three equations. It'll save you a lot of time on homework and tests.